Okay, so today's lesson is going to be a bit of a dense one, so just prepare yourself for that. We're looking at what we call SPDF notation. Now, this is kind of the introduction of the Schrodinger model of the atom, um, and sorry, the syllabus outcome should read models the atom's discrete energy levels, including electronic configuration and SPDF notation. Sorry, I'll have to change that on the slides before I upload them. So there's some revision questions at the top of page 39. Have a go at those. If you've done the answers here, sorry, if you've done them, here's the answers. So atoms contain protons, neutrons, and electrons. Atomic number is equal to the number of protons. Neutral elements have the same number of protons and electrons. Our electrons exist within shells within the atoms, and the outermost shell is called the valence shell. So, following on from the Bohr model and all the spectral line stuff that we've done, we're going to have a look at the Schrodinger model of the atom. So the Bohr model of the atom, it was revolutionary at the time, but it did have limitations. So it was a very one-dimensional model that used one quantum number to describe the distribution of electrons. And that was just the shell number. So it was 1n, 2n, 3n, 4n. And these arrangements, that in 1926, Erwin Schrödinger developed a model that used three quantum numbers instead to describe the way the electrons were arranged around the atom. So he reused Bohr's first one. These arrangements, we called them orbitals. So Bohr's one had shells, Schrödinger has orbitals. The first quantum number n described the size of the orbitals. So that was the shell. So n1, n2, sorry, 1n, 1, 2, 1n, 2n, 3n, 4n. That's the first quantum number. It literally just describes the size. So 1n is the smallest, 2n's a bit bigger, 3n's a bit bigger again. The next quantum number, L, describes the shape of the orbital. And the third quantum number, M, describes the orientation. Okay, so we're going to have a look at those three different quantum numbers a bit. Now, again, this bit's a bit dense. You don't need to know all of it, but we will do a bit of a mini summary halfway through so you get the important points out. So the first quantum number was the shells, so it's the same as the number described by Niels Bohr. Simply refers to which shell the electron exists in, how far it is from the nucleus. So n equals 1, n equals 2, n equals 3. As we go up, they're increasing in energy, and we fill them up from the lowest to the highest. So the second quantum number, the second quantum number refers to the shape of the orbital. Okay, these shapes are labeled S, P, D, and F, with S being the simplest and F being the most complex. So here's some examples of some of the orbitals. So an S orbital is a nice spherical orbital. P orbitals, we get these weird kind of dumbbell shapes, two clouds either side of the nucleus. D orbitals, we kind of get this four-lobed orbit of the electron. And F orbitals, they're kind of a weird eight-lobe. Some of them are barrel-shaped. Once we get onto the next part and look at the third quantum number, you get to see all the different shapes that are available. Okay. But yeah, so basically S is the simplest, F is much more complex. Now, the third quantum number. The third quantum number refers to the orientation of the orbital. Okay. Now, each orbital has a different number of orientations. So an S orbital, it's a nice sphere, so it can only be oriented in one direction. Okay, so it doesn't matter which way you hold the sphere, it's still a sphere. So it has one orientation. P orbitals have three orientations, so that's along the X, the Y, and the Z axis. D has 5 and F has 7. Okay, and the important part for our Schrodinger SPDF notation stuff is that each orientation can only hold a maximum of 2 electrons. So basically what this leads us to is that s orbitals can hold 2 electrons, p orbitals can hold 3 times 2, so 6 electrons, d orbitals can hold up to 10, and f orbitals can hold up to 14. Okay. Let's just have a look at the shapes. Now, you don't need to remember these shapes. This is just more for posterity's sake. So we've got our s orbital at the top. It's a nice spherical orbital. Okay. We have our p orbitals then. So we have the first ones oriented along the x-axis, then along the z, then along the y. And then they just start to get a bit more complex. So we've got our 4 lobe things. So with our d orbitals, we've got 4 lobes along x, y. Then we've got x, z. Then we've got this weird donut with 2 spheres. And then we have the z, y, and we have the x, y again. But it's slightly different. And then there's all those weird ones for f orbitals. They're just kind of way out there. And again, you don't need to memorize the shapes. Just know that they are quite complex. And that there's 7 different orientations and there's 2 electrons in each orientation. So here's our mini summary. So this will help us for the rest of the lesson. So basically, first quantum number describes the shell. Second describes the shape. S orbitals can hold 2 electrons. P can hold 6. D can hold 10. F can hold 14. Okay. So yeah, get that mini summary down. There's a little space to write at the top of page 41. Then we're going to have a look at actual SPDF notation. So all this information that we've got about the orbitals, we can actually write it down in a way that lets us, we can represent what orbitals are within an atom. Okay, so let's move on to that. So electronic configurations in the Schrödinger model. So here's a representation of the electronic configuration for the Schrödinger model of the atom. So giving you the example of chlorine here. Now, we've got all these weird numbers, letters, some superscript. What does it all mean? Well, the first number, it's broken up into lots of different things. So we write them all together, but basically there's 5 different orbital information things there. The number at the front, there's a coefficient represents the shell number. So this first bit of information tells us that there's some electrons in the first orbital, so the first shell. Then there's some in the second, some in the third. The second bit of information is a letter, and that represents the orbital, so the shape. Okay, so we have an s orbital there, so remember they're our spherical ones. And the superscript number represents how many electrons are in that orbital. Okay, so basically with putting all that information together for chlorine, we have in the first shell there is an s orbital with 2 electrons. In the second shell there is an s orbital with 2 and a p orbital with 6. In the third shell there is an s orbital with 2 and a p orbital with 5. Okay, so that's where all that information comes from. Sorry, that's what all that information means. So, starting to put it all together. So when determining the electron configuration of an atom, there are several rules we need to follow. So firstly, it was that thing we covered in the mini summary. So s orbitals can hold 2, p orbitals can hold 6, d can hold up to 10, and f can hold up to 11. The second thing is that the first shell only has s orbitals, second shell only has s and p, third has s, p, d, fourth has s, p, d, and f. Okay. Yeah. And the third one is that the orbitals fill in a way that does seem kind of odd at first, but once we start to get a bit deeper into the understanding of it, it does become a bit more clearer. Okay, so let's have a look. This is how they fill. So I've actually given you this diagram at the top of page 42. Okay, so if you ever asked, what is the electronic configuration of this atom, and you're not sure which way to fill them, this is how we do it. So we just write them out in this nice grid, and we start drawing a line from the top right to the bottom left, like that. And then we follow it and go through the next one. Same thing, go through the next two. So it basically fills 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, so on and so forth. Okay, so they feel like that. Now, that relates back to what I showed you very early on with the shells, how once we start getting past the third period, the outer shell will be full, but it will start filling up shells that are more towards the middle. Okay, and this is the reason for it. It's this Schrodinger model of the atom. Now we can relate that. Yeah, so it's easy to see this filling order when we transpose this info onto a periodic table. So that's why I've given you a nice blank one there. Before we go much further, so you don't have to write this one. Actually, sorry, yeah, you don't have to write this exact information down, but we'll write it in a better way. Basically, the periodic table is split into what we call blocks. This part up here, this is what we call S block, and it includes hydrogen. Sorry, it includes the helium over here. Okay, again, because that's the first period, it's a bit weird. So helium is technically in S block, even though it appears over at the top of P block, which is our next one. So all of these elements are P elements. We call that P block. Transition metals, they're D block elements. And the ones down the bottom, the lanthanides and the actinides, they are F block elements. Now, when we're trying to determine the electronic configuration, we can use this in conjunction with the shell number. Okay, so if we have a look at S block, the top row on S block is the 1s orbital, then it goes 2s, 3s, 4s, all the way down. Now, remember in the first orbital we only have s, so in the second orbital we have s and p, so that's where we go over to p block, and we start at 2p, go 3, 4, 5, 6, 7p. Okay, so they kind of line up. Now this is where things start to get a bit weird. When we start filling up the d orbitals, so it'll be, in this fourth period we've got 4s orbitals, they actually become 3d. Okay, so it's not exactly equal to the period that it's in. It goes into a different shell. Okay, so even though elements in this 3d block, so things like iron and zinc, even though they're in the fourth period, the orbitals are 3d orbitals. Okay, so it goes down by one effectively. And the same thing with these lanthanides and actinides. We have 4f and 5f. Even though they start in the sixth period, they start filling 6s orbitals, then the 4f orbitals, then the 5d, then the 6p. Okay, so it is a bit weird, but it can be understandable. Okay, we can use this information. I think in an exam situation, you probably won't be asked to do the electronic configuration of anything past here. Okay, that's just a feeling. I don't have any evidence to back that up. But as long as you can understand how to fill up to there, it should cover you for most bases. Okay. So how do we actually determine these electronic configurations? So let's go through an example. Determine the electronic configuration of sodium. Now we want to do all that 1s, 2s, all that sort of stuff. So how do we do that? Well, what we do, we determine the number of electrons in sodium. So it just said sodium, doesn't say it's an ion or anything like that. So we have a look on the periodic table. Sodium has a atomic number of 11, and it's neutral, so it's got 11 protons, so it should have 11 electrons. Okay. Now, we start filling the orbitals, starting with 1s until you get to 11 electrons. So we use that one of those two diagrams at the top of page 42 to help us fill them up until we get to 11 electrons. So I've got it here. First things first, we start with the 1s orbital. 1s can hold a maximum of 2. Okay, so we're going to say that that's a 1s2. I think I'll just write it at the top here for you. Okay, so the 1s orbital can hold 2, so we put the 2 in superscript. Now, yeah, so next we fill up the 2s orbital. 2s can also hold 2, so we say 2s2. So far we've used 4 electrons, so we need to keep going up until we get to 11. Next is 2p. 2p can hold 6, so we're going to say it's 2p6. And we're up to 10 electrons. Now sodium only has 11. So the next orbital that we fill is going to be the 3s, but it contains it cannot only contain 1 because we've only got 11. So we're going to say that the next orbital is 3s1. Okay, and so that's the electronic configuration for sodium. So we're putting it together. So 1s2, that's the first one we filled. 2s2, so now we're up to 4. Now we're up to 10, that's 11. Okay, so that is then the electronic configuration of sodium. Now, moving on. Example 2. Determine the electronic configuration of iron. So the first thing we have to do is figure out how many electrons are in iron. So iron has, its atomic number is 26, I'm pretty sure. Let me just check. Yep, 26. So again, it's a neutral atom, so we don't have to change the number of electrons. There's none lost, none gained. So it's neutral iron. It's got 26 electrons, so we have to start filling them up. Okay. We start with 1s until we get to 26. So following the same thing. So 1s can hold a maximum of 2, so it's definitely going to be 1s2. That one's filled. 2s2. Again, we've still got plenty. We're only at 4 electrons out of 26. Fill our 2p, so we've got 2p6. Next, follow the our little curvy thing. It's next going to be 3s. 3s can hold a maximum of 2, so it'll be 3s2. We can then start to move on. What's next after 3s? We follow our line. It's going to be 3p. So 3p can hold a maximum of 6. So if we add that on, we're now at 18 electrons. 4s, which is next, can hold a maximum of 2. So we go 4s2. So we're at 20, so we've got 6 left. So the next orbital that we fill, if we follow the line, it's going to be the 3d orbital. Now that can hold a maximum of 10, but we've only got 6 left. So we're going to say that that orbital is 3d6. Okay. And so we're at 26, that's where we stop. So we put that all together. So iron is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2. Now, when I was writing it on the page before, I had the 4s before the 3d6. That was just as we were figuring it out. When we actually write it, we prefer to put the coefficients in order. Okay, so we put them by the first quantum number, which is our coefficient, then the second quantum number, which is the s's and p's. So we do s, sp, spd, spdf. Okay, so that's our electronic configuration for iron. So what I want you guys to do is have a go at determining the electronic configurations for boron, aluminium, and bromine. Okay, so there's spaces to do these in your workbooks on page 43, 44. So just do the same things that we've been doing. So figure out the number of electrons first, and then start counting them up through that through the lines. So, 1s, 2s, 2p, 3s, etc. Okay, so let's just pause the video here. I might just put that, hold on, let me go back and I'll put the thing up. Yeah, I'll just show you that one. You can read it. There's one in your booklet at the top of page 42, but I'll just put that there as well. So yeah, so do those three, pause the video, and we'll come back for the answers. Okay, so the answers. So for boron, hopefully you got 1s2, 2s2, 2p1. So boron is atomic number 5, so it should have 5 electrons. Nice and easy to fill just through the 1s, 2s, 2p orbitals. Next is aluminium. So aluminium has a atomic number of 13. So all of them should add up to 13. So follows that pattern there. And bromine, bromine's a bigger one. It's 35. So hopefully that's the answer you got there. Okay, so it should have a full first, second, third shell going into the fourth with 4s2 and 4p5. Now, if you didn't get those, come and see me. Put your hand up. Well, actually, no. If you're at home, don't put your hand up. Uh, Come and see me, and we'll go through it and try to make sure you understand what's going on. As for the rest, here's a summary. Um, so electrons are organized into shells, then orbitals. The orbitals are labeled S, P, D, and F. S are the simplest, F being the most complex. S orbitals can hold 2 electrons, P can hold 6, D can hold 10, F can hold 14. Okay, so that's it for today. Make sure you get that down. Do the questions on page 45. And yeah, that's all for today.